Working with complex numbers. Before we can work with complex numbers, we can talk about what is a complex number. And a complex number is where you have a and a B and a I and I guess it really doesn't make very much sense. A complex number is written in the form A plus BI. A and B are real numbers, and I is going to be equal to the square root of -1. And that's what we're learning now. The imaginary number, so the complex number is, the complex number has a real number, and it also has an imaginary component. So an imaginary number is a number in the form of BI. So this is my BI, where B is the real number and I equals the square root of -1. And then, so that's the identification of a complex number. And we want to be able to represent square roots of negative numbers as multiples of I, and represent complex numbers in the form A plus BI, or in the complex plane. So we will also graph these complex numbers and simplify powers of I using their cyclical nature, and determine the absolute value of a complex number. Okay, so irrational numbers. Let's start there. If you recall, we have a real number system, and in our real numbers we had rational numbers, which we covered pretty extensively up until now, where we talk about you have your natural numbers, which are going to be 1 and up. Your counting numbers 1 and up. Your whole numbers would include all your natural numbers plus adding 0. Integers will include your positive and negative numbers along the number line. And then rational numbers are any number that can be written as a fraction. Those are one portion of my real numbers. And then we have the irrational numbers, which cannot be expressed as a ratio of whole numbers. Most commonly seen is pi, and maybe you can do a square root of 2. It's not something that you can necessarily calculate in your head. You're going to need the calculator to do something like that. So our irrational numbers, and that's what those are. Just remembering that number system. So when we look at simplifying a square root, and we're going to learn to simplify our square root because remember that I, as we learn, I is going to be equal to the square root of -1. And we have to get to the point where we can find the square root of -1. So when we go to simplify a radical, we learned in algebra that if we have something along the lines of the square root of 16, well, that's just going to be 4 times 4. So the square root is 4. But when we have the square root of 27, that is not a perfect square. So we learn how to simplify that root down to the smallest radical we can. So this would be the same thing as the square root of 9 times the square root of 3. And to rewrite that, we could say, hey, the square root of 9 times the square root of 3. So therefore, when I go ahead and I do this, it's going to become 3 times the square root of 3. And I was able to simplify that radical. And in doing so, we learn how to... So in simplifying that radical, we were able to remove all perfect squares, basically doing as much as we could, basically in our head, to get to a point where we can not use the calculator, because quite honestly, the square root of 3 is more accurate than putting in a decimal, because you would end up rounding and it would not be accurate. So that is simplifying a radical. So as we get into the imaginary number, we were never able to find the square root of -9 before now, because we always said that in order to find the square root, you had to have the same number times itself. And you can't multiply a number times itself and get a negative number. So what we do is we learn to simplify our radicals by removing that negative 1. So that can be rewritten as the square root of 9 times the square root of negative 1. And if I go ahead and simplify that a little bit more, I have the square root of 9 times or break it down a little bit more, square root of negative 1. And the square root of 9 we just said was 3, and then we have the square root of negative 1 remaining. Well, if you see, the square root of negative 1 we're going to learn is represented by the I. So we can replace I with square root of negative 1 with I. So come down here, that is going to be equal to 3 times I. So anytime you see I, you know that it is the square root of negative 1. Again, up until now, we've never been able to find the square root of a negative number, but this is allowing us to do that. And to step back from that for a moment, remember that when we graph a parabola, we would say that this parabola had 2 solutions. This parabola had 2 solutions. This parabola may have only had 1 solution, right, because it touched one time. And then we said this solution, the parabola that does this, has no solution. And actually it has no real solution. It is going to have an imaginary solution. So that quadratic does have a solution, just it is not a real number. So that is where we are going to start working here. So that is sort of like the big picture of where we're going to start tying this number into, or this concept. So as I get rid of this, we can go ahead and simplify a few here as an example. So if I want to find the square root, let's see, what can I do? 56? Square root of negative 56? And then, so if I were to simplify that, that would be the same thing as the square root of, negative 1 times 28 times 2, or the square root of negative 1 times the square root of, 28 really doesn't do me any good, right? I need a perfect square, so that could have also been 4 times 14, I believe, is 56. So if I simplify that, I get the square root of negative 1 times square root of 4 times square root of 14. And when I simplify that, the square root of 4 is going to be a 2. The square root of negative 1 is going to be an I, and then we can't find a perfect square left in there, so that's going to remain a 14. So that is simplifying a radical with a negative number in it. And I was able to do that without utilizing a calculator because I was just working with my perfect squares. And again, possibly the square root of negative 16 is going to be the square root of 16 times the square root of negative 1. And then we know that square root of 16 is going to be a 4, and square root of negative 1, or we said, hey, for I, because I is equal to the square root of negative 1. So there we go. There we're simplifying square roots. Now as we, now I just did this example right here where what is the square root of negative 16? So the square root of negative 16 is going to be 4i. Simplifying that radical. But we start talking about the sums. What is the sum of these two? Well, when we have radicals, we need to make sure that we have like radicals in order to add. Right now, just to look at it, I cannot add the square root of negative 2 and the square root of negative 18. But if I'm able to simplify the square root of 18, I may be able to. So as I look here, the square root of negative 2 is going to be the square root of 2. And then if I look at the square root of 18, negative 2. Negative 18 is also the square root of negative 1 times 9 times 2, would give me negative 18. And you'll notice that I have this perfect square. So if I reorder that because I wrote it poorly, 9 times negative 2. So the square root of 9 is going to be 3, and I'm going to leave behind a negative 2. So remember, we were adding this, right? We said the sum of the square root of negative 2 and the square root of 18. Well, if you remember, right, I have a 1 square root of negative 2 plus a 3 square root of negative 2, which gives me a 4 square root of negative 2. Now, however, I don't want to leave the negative 2 in the radical, so I would rewrite that as 4 times the square root of 2i. Why? Because remember, the square root of negative 2 is equal to the square root of 2 times the square root of negative 1, and then we know that that's I, so we would have square root of 2i. So there you go. There's my better answer. Let's see, what else can we do as we talk about finding the square root here? Complex numbers, okay. We're going to look at some stuff here, but a complex number, remember, has a real component and an imaginary component. And when you graph that on the coordinate plane, you're going to have your real numbers along the x-axis, your imaginary numbers along the y-axis, and that's why I have I labeled here, because it's traditionally our y-axis, but in this case it's I. So now I want to look at remembering some of the stuff here, that if I look at A, the ordered pair for A is going to be, it looks like negative 3, negative 2. Okay, so this is my I column, and this is my real number column. So I would rewrite A. Point A is negative 3, negative 2, which equates to, in a complex number, would be negative 3 minus 2i. Here's my real component. Here is my imaginary component. And I go around and look at B. B is going to be equal, or coordinate is going to be 3, negative 1. So B is 3, negative 1, which that is going to be my real number 3 minus I, or minus 1i. So there is my complex number. Come here to C. C is going to be 1, 2, 3, 4, 4, negative 1, 4. So when I convert that into a complex number, that is going to be negative 1, 4 is going to be negative 1 plus 4i. Okay, again, I'm just writing it into the complex form. And D is going to be 1, 2, 3, 4, 5. 5, 1, 2, 3, 4, right? 4. So 5, 4, and that is going to transform into 5 plus 4i. So that's how you come up with the complex number. When you're doing the mapping portion of it, your what used to be your y-axis is now your imaginary axis. You have your real axis, and so that's what you're looking at. And I guess what's left, how do I identify the distance? Okay, how far is it? The distance is absolute value from the origin, because that's what we're trying to calculate here. We're trying to calculate the distance of these points from the origin. And if you notice this thing right here, this says the absolute value of your complex number, a plus bi, is equal to the square root of a squared plus b squared. So you may recognize this as the old looks sort of similar to the Pythagorean Theorem, where we would have a squared plus b squared equals c squared, and then we would find the square root of c. So that's sort of what a plus bi is. It represents that square root of c. So in doing so, all we have to do really is just knock some substitution out here. Okay, so in calculating this distance, of course, it's going to be the absolute value of b plus a plus bi is going to be equal to the square root of a squared plus b squared. So this is going to be my a value, this is going to be my b value, and then we're just going to fill it into the square root. So looking here, it's going to be my a, my b. So I have the absolute value of negative 3 minus 2a, or 2I, is going to be equal to the square root of negative 3 squared plus negative 2 squared, which is going to be equal to the square root of 9 plus 4, which is the square root of 13. And that's as simplified as we can get because there is no perfect square in there. Looking at this next one, we have the absolute value of 3 minus I is going to be equal to the square root of 3 squared plus negative 1 squared, which is going to be the absolute value of 9 plus 1 is the, absolute value, square root of 10. So I'm just finding some substitution here, doing some substitution to find the distance from the origin. Let's see what else we got here. We have the absolute value of negative 1 plus 4i is equal to the square root of negative 1 squared plus 4 squared. It's going to be the square root of 17, right? We'd have 1 plus 16 is 17. And then finally, this last problem, we have the absolute value of 5 plus 4i is equal to the square root of 5 squared plus 4 squared is going to be the square root of 25 plus 16 is going to be the square root of 41. And that is the distance from the origin for those complex numbers, calculating the distance. One last thing to cover is the cyclical aspect of an imaginary number. So if we start off with I, I is, it is equal to the square root of negative 1, but I is equal to I. I squared is going to be equal to the square root of negative 1 times the square root of negative 1, which is going to be equal to negative 1. Then we have I cubed, which is going to be I squared times the square root of negative 1, which is going to be, as we said, I squared was negative 1 times I, which is going to be negative I. And then we have I to the fourth, which is going to be I squared times I squared, which we said that I squared is this thing right here. So that is going to be negative 1 times negative 1, which is going to be 1. Now, what we will find is we will start to see it repeat. So if I go I to the fifth, that is going to be I to the fourth times I to the first, which is going to be 1, right? Times I, which is going to be equal to I. There you go. That's our starting to repeat right there. Let's look and see what I to the sixth is. Well, that is going to be I to the fourth times I squared, which is going to be, I think we have negative I, negative 1, and then we have 1, which is going to give me a negative 1, and again, starting to repeat. And then I to the seventh is going to be I to the fourth times I to the third, which is, we said I to the fourth is going to be 1, right there, times I to the third, which is going to be negative I. So this is going to be equal to negative I, and again, starting to repeat. And then I'll just tell you that guess what? I to the 8th is going to be equal to 1 because it starts to repeat there. So you can use the cyclical nature of I to find higher orders of your exponents.